Hello guys, this is Prime Concept. In this video, I want to focus on the derivation for refraction at a single surface, right? So we want to consider lenses, just one surface of a lens. When light refracts through only one surface of a lens, what would be the relationship? We want to derive it in this video. And this relationship is known as Gaussian formula for a single surface. Now, the reason why I want to derive this is because I'll be needing this relationship to derive later what we know as the lens maker's formula, the formula that is used to calculate focal length when those that are producing lenses are trying to produce lens. Every lens, like we know, has a determined focal length. So those that manufacture these lenses, how do they calculate the focal length? So we're going to learn how to derive that formula and how to apply it later. So, but for us to be able to do that, we need to understand refraction at a single surface, the Gaussian formula for this. So let's go quickly into the business. But meanwhile, if you have been watching my videos and you are yet to subscribe, please do well to hit the subscribe button so you'll be getting more valuable contents from me. Like my videos whenever you come across them, and then comment, then share with your friends. Thanks. Now, say we have a single refracting surface like this. Let me try to minimize the diagram. So this is a single refracting surface, which is a convex surface. And then I have my principal axis, which is going to be a paraxial ray, that line. So if I have a point object at this point, which I would call O, so if ray emanates from this object, it will hit my surface at some point, this, and then because this is a refracting surface, when it hits the surface, it will bend, it will refract, and so it refracts like this. And this point is where your image would be formed, right? Now, if since we are considering refraction, there will be need for us to indicate the normal so that we can identify the incident ray and the refracted ray. This is our incident ray, this is our refracted ray. It means we need to have our normal. So this is our normal, right? Now, so that this angle, I'm going to call it I, and then this angle, I'm going to call it R. Now, you remember that when you draw a normal is a line that makes an angle of 90 degrees with the surface, right? So it means that if this is your normal making an angle of 90 degrees with the surface, the normal should definitely pass through your center of curvature. Because when you draw any line from the center of a circle to any point on the circumference, that line makes an angle of 90 degrees at the circumference. So it means that this point here should be my C, center of curvature for this surface, right? Now I'm going to label this diagram. I'm going to call this angle. I'm going to call it alpha, call this angle beta, then call this angle theta. Also, I want to create a height so that I can have some separate triangles here. So I'll call this height H. So I believe you can see this thing. So bear with my space. Now see what we want to do. We want to consider one of the things we know for triangles, that the exterior angle, which is I, is going to be the sum of the opposite interior angle. So if I consider this triangle at this point, at point O and at point C, right? Let's say I'm calling this point M. So if I consider triangle MOC, it means that the exterior angle is angle I, which is the incident angle. It's going to be the sum of alpha plus beta. So I is going to be alpha plus beta. Now, in same way, if I consider triangle M, C, and I, it means that the angle exterior is beta. Considering triangle MCI, the exterior angle is beta, which is equal to R plus theta. So in that case, I'll have that beta, let's call this equation 1. I'll have that beta is equal to R plus theta. But then I want to make R the subject. So I'll have that R is going to be beta minus theta. So I'll call this equation 2, right? Now, also, if you recall from my previous videos when we studied refraction at plane surface, we mentioned the concept of optical invariant. So applying optical invariant here and knowing that this is my first surface with refractive index N1, this is my second surface with refractive index N2. Now if I apply the concept of optical invariant, or you can still say Snell's law, I would have that N1, let me still manage this space. So I'll have N1 sine the angle in the first surface, or in the first medium, which is I, sine I, equals N2 sine of the angle in the second medium, which is what now? R, right? Now, since we are considering that this ray is a paraxial ray, it simply means that we can make the assumption that sine I is approximately going to be equal to I, right? Yes, for small angles. So we also can make the assumption that sine R is approximately going to be equal to R. So that if this is true, I can come back to this equation, which is equation 3. I can come back to equation 3, and then I would have N1, instead of sine I would now have I equals N2. Instead of sine R, I would then have R, because they are now approximately equal. So if I replace I with equation 1, I would have that N1 is going to give me I, which is what now? Alpha plus beta equals N2, and then R is going to be what? Beta minus theta. I'm going to expand this. So if I expand, I'll have this going to be N1 alpha. This is going to be N1 beta. This is going to be N2 beta. This is going to be N2 theta. Now what am I going to do? I'm going to collect like terms so that this will come and meet this. Remember, this is N1, so that this will go and meet this. Let me bring this here. So I would have N1 alpha plus N2 theta when this comes. It's going to give me what now? N2 beta. When this goes, it becomes minus N1 beta. So that I would come back to this diagram considering the triangles, this triangle with this height, right? And if I consider that, I would quickly see, let me factorize it and I'll come back to this. So I have N1 alpha plus N2 theta equals, you can see that beta is common here, right? So I would have N2 minus N1 into what now? Beta. I'm trying to manage the space so that I won't draw, but I'll still have to rub this. Now considering this triangle O, M, and at this point, so you would notice that alpha is going to be opposite as sine alpha, which is same as alpha now from our assumption. So sine alpha is going to be opposite height h over the hypo. Now since this is your object, it simply means that the distance from this point to this point is u, your object distance. Then the distance from here to this point C. Remember, C is your center of curvature, so this is R, the radius of curvature. Also, the distance from this point to this point, since this is our image, is V. So that if we consider sine alpha, it's going to be the opposite, which is the height h over the height opposite, sorry. With my rubber. Okay. Yeah. So we want to consider cos, because we need this. So cos alpha is going to be opposite, and alpha is going to be opposite, which is h over my adjacent, right? So opposite h over adjacent, because I want u, right? That's why I'm considering tan. So it is tan, not sine or cos, that will give me h and u, because I need u, right? Now, so alpha or tan alpha is h over u, and tan alpha is approximately same as alpha from this assumption also. Now, but since our object is on the negative side, if you remember our sign convention, it means I should attach minus to u. That is my sign convention. Now, if I consider the same thing for beta, watch, this is a triangle for beta. So beta is going to be opposite over the adjacent. So beta is going to be the height over the adjacent r, which is positive in this case, right? And then if I consider this angle theta, theta is going to be the opposite again, which is h over the adjacent, which is now what? V, positive, right? Yes. Now, if I substitute these parameters, if I substitute this into this equation, I would have, I want to replace alpha with this, I want to replace theta, and then so on. So if I replace alpha, I would have that n1 times alpha, which is now h over minus u, then plus n2 times theta, and our theta is h over v, is going to give me n2 minus n1, right? Yes, times our beta, and our beta, I think I've mixed this, n2 theta, okay, yes, and our beta is now h over r, so h over r. So what would happen here? Very simple. I would clearly have that my h, so that I don't waste more time. Notice that h is common here, right? You can factorize this h, and then it will cancel out this h, so that on this side I will be left with n1 over minus u plus n2 over v equals what? n2 minus n1 over what? r, because h would have cancelled out. So that if I write this properly, I would have, can rearrange this so that this minus will come here. So I would have n2 over v minus n1 over what? U equals what now? n2 minus n1 over what? R. So this formula I have arrived at. This formula is what we know as Gaussian formula for a single surface, which is n2 over v, image distance, minus n1 over u, image distance, object distance, equals this. Now, what are the points you should note about this formula? If you want to use this formula, one of the things you should note is that you would always need to take the absolute value of the difference in the refractive index. So it should always be positive. So meaning that n2 minus n1 should always be positive. Now say you do n2 minus n1 and it gives you minus 1. It means you're taking the positive value. So that's why the absolute value is necessary. That's one point you should note when using the Gaussian formula, right? Now another point you should note when using this is your radius of curvature, right? So if you are dealing with a convex surface, just like what we have considered, a convex surface, then it means that your r should be positive for a convex surface. Now if you are dealing with a concave surface, your r should be what? Negative. So these are conventions you should take note of, while you know our convention for image and object, right? So I've said that image, if image is formed on the right hand side, it is positive and real. If it is formed on the left hand side, then it is what? Negative and what? Virtual. So take note of this convention. So put them down so I don't take time writing them again, right? One is that you take the absolute value here. Two, you're dealing with a convex surface, r is positive. Dealing with a concave surface, r is what? Negative. R is your radius of curvature, and then your image and object distance follows similar conventions for the lenses we have already established. So I believe this concept is very clear to you. So if you enjoyed this derivation, do well to hit the like button, the subscribe button, and share with 10 of your friends. Tell them this is prime concept. Thank you.